Okay. Now we are going to do the AP 1.6, the photoelectron spectroscopy. This is one of the most important uh, chapter in AP because I see that this question comes almost every year, and you should know this very clearly. Okay, so understanding this concept is very important in Unit 1. For photoelectron spectroscopy, what they use is they use a high energy photon to remove electrons from all the shells from an atom. Earlier, we talked about what is called as the mass spectroscopy. Mass spectroscopy, you take any element in a solid form. Okay, first you heat, it becomes a liquid, and then it becomes a gas because the phase changes happens first. And then it becomes an ion, and then it loses the first electron. The first ionization happens. Okay, we stop there because we take the sodium ion, and then that's how the mass spectroscopy is done. Okay, so only the first electron is removed. Okay, to understand how many isotopes are there, okay, to isotopic abundance, calculate those things, mass spectroscopy is used. But photoelectron spectroscopy is you do the same thing. You take a solid, and then after the phase changes, you take out almost all the electrons. So electronic configuration is 1s2, 2s2, 2p6, 3s1. So there are 2 electrons in the first shell, and there are 8 electrons in the second shell, and then 1 electron in the outermost shell. So you spend a frequency of photon, okay, and then you try to pump out all the electrons. So the ionization energy is calculated using the amount of frequency, the frequency of the photon, minus how much kinetic energy of the electron that comes out with. Okay, based on that, the relative number of electrons versus ionization energy, that is that we have to spend for 1 megajoules per mole, if a graph is drawn. So the graph is drawn like this. So the first electron is going to come out as 3s1, followed by all the 6 electrons, and then the 2s electron, and then the 1s2 electron. So this tells us that how many orbitals are there. So this clearly tells you this is 3s1, this 1 electron is 3s1, and then the 6 electrons, and then these 2 electrons, and then these 2 electrons. So 3s first, 2p6, 2s2, and 1s2. So if it is for boron, boron is atomic number 5, it is going to look at as 2p1, 2s2, followed by 1s2. If it is carbon, it is going to have 2p2, 2s2, followed by 1s2. But when you look at this, see how the graph is being drawn. The reading the photoelectron spectrum is very important, right? The cipher is very important. So first is deciphering the electronic configuration for us. Okay, the area under the curve is nothing but the number of electrons. Okay, so here I know that there is 2 electrons. Here I have 2 electrons because they have the same height. The area under the curve is same. Now I have 6 electrons here. Okay, now I have this one, it looks smaller than this. So I should have, if this is 2, this is roughly 1. Okay, but if this is 1, then I know that this is full. Okay, that's very important. Okay, so the area under the curve tells you number of electrons. That is number 1. And then when you have a smaller peak, that means the previous peak is already full. Okay, so 2p6. It cannot be 2p5. Okay, and close to nucleus, the more that is close to nucleus, it has higher energy to remove. Okay, we are going to spend more energy for this compared to this one. Okay, we are going to spend less energy for this. Okay, the electrons have high energy when they are far away from the nucleus, right? They are very far away from the nucleus. They are not attracted, so they can spend and they can revolve much faster. The understanding, if hypothetically, if I have to write between three models that we have in shell model, photoelectron spectrum model, and quantum model, this is how it's going to look like. This model is what we look right now. So we saw that this is 1s2, 2s2, and 2p6, and then 3s1. If it is just a shell model, sodium has only three shells: 1s, 2s, 3. So it should have only three peaks: 1s2, and all the 8 electrons should look like this, and then 1 electron. So it should look like 2, 8, 1. Here it shows as 2, 2, 6, 1. Here, if it is a quantum model will split like in the orbital diagram. Okay, the earlier orbital diagram that we looked here, okay, here like this. So it will split each and everything will look as 2. So 1s2, 2s2, all the p's are also 2px2, 2py2, 2pz2, 3s1. So it will look like this. It is an hypothetical uh, understanding for the as a graph. Okay, but that is the reality. Okay, so it is just I'm just trying to draw that such a manner that you try to understand. If you draw a graph for shell model and quantum model, that's how it's going to look like based on the photoelectron spectrum model. But understanding this is very, very important, because several, at least couple of questions comes every year from my understanding. So this is important. Reading the graph. If a graph is given, you have to identify the element. Okay. If the element is given, you have to be able to draw a graph. Okay. So this is very important. This is all the 1.5 and 1.6 of